Hey, this is Mrs. Mays, and you're here to balance complex redox reactions. These can't be balanced the normal way, so I'm going to show you some tricks. First of all, remember that oxidation reduction reactions involve the transfer of electrons from one element to another. Here's an example. Aluminum reacts with oxygen to form aluminum oxide. In other words, the elements form an ionic compound by the transfer of electrons from the metal to the nonmetal. And we have special words for this. Oxidation refers to an element losing electrons. And so we have an acronym about Leo the lion, right? And reduction is when an element gains electrons. So we use this acronym to help us. Leo says grr. So what we find in this reaction is that each aluminum has lost 3 electrons because aluminum makes a 3+ charge to get a stable configuration in its electrons. The oxygen will each gain 2 electrons so that its configuration can become like a noble gas. And that's how we form the ionic compound aluminum oxide from its elements in a redox reaction. But not only do we have to balance the atoms, we also have to gain electrons that have been lost with the electrons that were gained. You can't lose electrons into nowhere. They have to have a place to go. So let's take care of the oxygens. To balance the oxygen, I have, 2 and 3. So let's make that equal to 6 oxygens on either side. And that gives me 4 aluminums to balance the equation. But let's see how the electrons work. Each aluminum lost 3 electrons to form a +3 charge in the aluminum. And since there were 4 aluminum atoms, each losing 3 electrons, that makes a total of 12 electrons lost. The oxygen, as it reacted with aluminum, had a 0 charge to start with, but remember, oxygen forms a -2 ion. So that means each oxygen gained 2 electrons. That makes a total of 12 electrons because I have 6 oxygen atoms on both sides. So the electrons that were lost are equal to the electrons that have been gained. Be careful in redox reactions that you balance the atoms and you also balance the charges. So if we're going to balance the charges, then you have to know what the charges are, right? We call the charges oxidation states because sometimes we're dealing with covalent bonds where it's not a true charge, but it's just describing like how it has access to those electrons. That's the oxidation state. So don't be confused if we say oxidation state. It's a lot like charge. You can think of them kind of the same way for now. So to determine the oxidation state, we're going to apply these rules in order. First of all, atoms in their elemental form have an oxidation number of 0 because the protons and electrons are equal. This includes diatomic elements like our Brinkelhoff elements. Bromine is coming in pairs and that's going to have a 0 charge, right? Iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, all 7. The monatomic ions have an oxidation number that's equal to its charge. So if you find a monatomic ion on the back of your periodic table in your ion naming card, then the charge is the oxidation number. No sweat. The third rule is that oxidation has an oxidation number of -2 unless it's in peroxide. Watch out for those peroxides because then your oxygen has a charge of -1. So be careful with those ones. Hydrogen has an oxidation number of +1 when it is bonded to nonmetals. But sometimes the oxygen can bond to a metal, and when it does, it will have a -1 charge. Because metals are always positive, that hydrogen, though, it can either gain an electron to make 2 electrons total, or it can lose an electron and have none, and that works just as well. Halogens are usually a -1, unless they're combined with oxygen. Then they will have a positive oxidation state. The sum of the oxidation numbers will equal 0 for a compound, or the value of the charge if you're dealing with a polyatomic ion. So those are the rules. Let's apply the rules to determine the oxidation number for each element in sodium sulfate. So we know that sodium sulfate has a total charge of 0 because it's an ionic compound, and compounds have to add up in such a way that it cancels out all the charges. Let's start with the sodium. What's the charge of sodium ions? It's a +1 charge. And since the oxygen is not in peroxide, we know the charge of our oxygen is a -2. The sulfur is the thing that I'm not sure what its charge is, so I'll put an X there for now. But I know that when I add 2 sodiums with 4 oxygens and 1 sulfate, I have to add up to 0. So I put the charges of sodium and the charges of oxygen in, and we figure out using simple algebra what the charge of sulfur has to be. So let's see, 2 plus -8 gives me -6 plus X equals 0. Therefore, X must be a +6. So in sodium sulfate, the charge of sulfur is +6 overall. So that's how we determine the oxidation number of the elements in a compound. Most of the things are going to be easy because they're in your list. There's sometimes going to be one of the substances, one of the elements that you have to use algebra for. We'll practice that as we continue on with the podcast, because now we're going to balance a redox reaction in acidic conditions. If the conditions are basic, then we'll worry about those in AP chemistry. For now, let's just deal with acidic conditions. First, we divide the chemical equation into half reactions, where we keep track of just one element at a time and see what's being oxidized and what's being reduced. Then we'll balance the half reaction first by balancing any element other than hydrogen or oxygen. We leave those ones for the end. Then I'll balance the oxygen by adding water molecules. The water is going to be in our acid because the acid is an aqueous solution. Then we balance the hydrogen by adding hydrogen ions, which are coming from the acid. That's what that pH factor is all about. It's about how many hydrogen ions there are in the acid. So it's okay to add water and hydrogen because they're in the solution too. Then we balance the charge by adding electrons as a reactant for anything that was reduced, or as a product for anything that was oxidized. Then once we know where the electrons are, we may have to multiply the half reactions by some whole number so that we can get the number of electrons to be the same in each of the half reactions, because the electrons that are gained must be equal to the electrons that are lost. Then we add the two half reactions together and we cancel out like terms. Something that shows up on both sides of our chemical equation, we can cancel out. Then finally, in the end, we double check the answer to make sure that all of the atoms and all of the electrons or charges are balanced. So that's our steps, and it will make more sense as we work them through. So let's take some time and work through an example. In this example, I have permanganate reacting with oxalate to form manganese 2+ ions and carbon dioxide gas. So let's break this out into half reactions. We're going to keep track of what happens to manganese, first as permanganate, and then later as the manganese ion, the 2+ form. And then we also need to keep track of what's happening with carbon in the oxalate ion as it turns into carbon dioxide gas. So our starting place is to write the half reactions, and usually when you have two reactants, then you just write a half reaction for each of them. Okay, what's next? Do you remember? Right, we have to balance everything that's not oxygen. So I look at my manganese, that one's okay, one on each side, and then I look at my carbon. I have 2 here, so I need 2 carbon dioxides over here. The next thing to do is balance the oxygen by adding water. So I have 4 oxygens in permanganate. That means I'm going to have to add 4 waters. One tip, by the way, start balancing in the middle of your paper. Don't start writing your equations on the left-hand side of your page like you're used to. Put everything in the middle, because now I have to go back to the left and add things over here on this side. So let's see, I added 4 waters. That makes 8 hydrogens that must also be balanced. So I'm going to put 8 hydrogen ions over here. Don't forget the plus sign because they're charged particles. They're not hydrogen atoms. They're hydrogen ions. Alright, what's next? Let's look at charges. We have to balance the charge. So in manganese ions, I know it's a 2+, but as permanganate, I'm not real sure what the charge of manganese is, but I do know it has to add up to a -1 overall because permanganate has a -1 charge. And there are 4 oxygens that each carry a -2 charge. And then there's 1 manganese atom that I don't know what the heck its charge is, but we're going to figure it out. So I have 4 minus 8 equals -1. That means X must be equal to +7. So my manganese in permanganate is a +7, and then it turns into a +2. That's a difference of 5, right? It went down by 5. Going down is reduction. That means I get to add 5 electrons as reactants because they lowered the charge of my manganese. So we know manganese is the thing that is reduced. Let's see, how do we oxidize the oxalate? So carbon, let's see, I don't know what the charge of carbon is in this particular ion, but I know the ion oxalate adds up to a total of -2. There are 4 oxygen atoms that each have a -2 charge, and 2 atoms of carbon that we don't know what their charge is, but we're going to figure it out. So I have 2x minus 6 equals -2. Oh, -8. I'm getting ahead of myself. Pardon me. That means 2x is equal to -6, and that, no, +6. That gives me x equals +3. So in oxalate, carbon has a +3 charge. So let's see what happens in carbon dioxide. Carbon dioxide is a molecule, not an ion, so it's going to add up to 0. I have 2 oxygen atoms that each have a charge of -2, combined with 2 carbon atoms, and I don't know what their charge is yet, but we're going to work it out. So 2x minus 4 equals 0. Is that right? No, that's not right, because I didn't have 2 carbons per molecule. I have just 1 carbon in the carbon dioxide molecule. I have 2 molecules of carbon, but I don't have 2 carbons per molecule. So that's why I was getting a little bit lost. Do you see that? CO2 is 1 carbon with 2 oxygens. Let's not make things harder than they need to be. I have a talent for that. Okay, then that means X is a -4. So in carbon dioxide, carbon has a +4 charge, and I'm going from a 3 to a 4. That's going up. So carbon is oxidized, just as we suspected. That means how many electrons? From a 3 to a 4, that's 1 electron, right? For each carbon atom, I need 1 electron to come away. But I have 2 carbon atoms to account for, so I better put 2 electrons in my equation so that I can get the electron away from both of them. Alright, well 5 and 2 are not equal, but I can make them be the same if I just multiply the top equation, the top half reaction, by 2, and then the bottom half reaction can be multiplied by 5, so that they'll each have 10 electrons, so that we can balance our electrons. So my top equation is multiplied by 2. 10 electrons plus 16 hydrogens and 2 permanganate ions. And I'm going to go ahead and add it to the next one. I multiplied my bottom equation by 5. So I have 5 oxalate ions in the bottom half reaction. Now let's take care of the products. Up top I have 2 manganese ions and 8 waters. And I'm running out of space. We'll put that down below. Plus I still have, let's see, 5 times 2 is 10 carbon dioxides and 10 electrons. So I have 10 electrons on both sides of the equation, which is good. We wanted those to balance, but I don't have to write them in if they're the same on both sides. They just cancel away. But that leaves me with a balanced equation. 16 hydrogens, 2 permanganates, 5 oxalates, 2 manganese ions are formed with 8 waters and 10 carbon dioxide molecules. There's no way that you could have balanced this by building a table and counting the atoms on both sides. The only way to balance this type of reaction is using the method of half reactions. But don't worry, if you're in honors chemistry and you get questions like this on your quiz, I will tell you to use half reactions, and I will also tell you what the products are. But let me show you how we might predict the products of an equation when we're given just words. So in example 3, we have an acidic solution of potassium dichromate added to a solution of iron 2 nitrate. So here's my clue that this is complex redox. First it says we have an acidic solution. That's kind of a dead giveaway that it's complex redox. Otherwise, they don't tell you it's acidic or acidified, they like to say. Dichromate is another giveaway. If you see the ions permanganate, chromate, or dichromate, then expect to do a complex redox reaction because those are strong oxidizers. Alright, well let's work this out. First of all, I want to remind you about spectator ions. Spectator ions in net ionic equations are the ones that are in the reaction, but they don't actually change. They don't do anything. And in this one, the spectator ions are potassium and nitrate. Remember the solubility rules that we learned? Alkali metals are always soluble, so potassium is just going to like dissolve in the water and hang out there and do nothing. Nothing's going to happen to potassium. The same is true for nitrate ions. Nitrate is always soluble. So it's hanging out there, but it's not going to do anything. So in our reaction where we have potassium dichromate reacting with iron 2 nitrate, we really have dichromate reacting with iron 2 because the potassium and the nitrate are just hanging about, not doing anything at all. We have to predict what are they going to form. So let's take on this challenge. Break it apart into half reactions and it won't be so bad. Start in the middle of your page. Dichromate, Cr2O7, has a 2- charge, and it's going to become chromic ions, Cr3+, in acidic conditions. And if we have iron 2, we have 2 options for the iron. One option is that it could become the atomic form or elemental form of iron with a 0 charge. The other option is that the iron might become the ferric, the metallic form, the higher of the charges, right? The iron 3. So our 3 options are 0, 2, or 3. Those are the only charges that iron takes on here. So which one is it? Quite frankly, I don't know. So I'm going to wait on the iron. I'm going to see what's happening with the dichromate first, and then we'll decide what to do with the iron based on what's happening to chromium atoms here. So let's evaluate the charge first. I know that dichromate has a -2 charge overall, That comes from 7 oxygen atoms, and those each have a -2 charge. And then the chromium is what I don't know, but I do know that there are 2 of them in dichromate. So I'm going to call that 2x. Let's solve for x. 2x minus 14 is -2, so 2x equals 12. Therefore, each chromium is going to be a +6. Okay, well, what I see is my +6 got reduced to a +3. So I'm adding 3 electrons for each chromium. There's 2 of them, so 3 times 2 is 6 electrons overall. And that leaves me 2 chromium 3+ ions on the other side. Now that I know that chromium is being reduced, I can decide to oxidize the iron. It's got to go up because chromium went down. So I'm going to make my iron 2 become iron 3. How many electrons is that? To go from a 2 to a 3, we had to lose just 1 electron, right? And 1 electron for each atom. The atoms are balanced, so we're good. But 1 and 6 are not the same. That's not a big deal. I'm just going to multiply the bottom equation by 6, and then I still have to take care of oxygens up here. So let's balance the oxygen in the first half reaction. I have 7 oxygens in dichromate, so I need to add 7 waters. And when I add 7 waters, that makes 14 hydrogens that have to go back on this side of the equation. So let's put 14 hydrogen ions in place. There we have them. Now I have 6 electrons in both because I'm multiplying my bottom half by 6. Everything is balanced. Let's add the 2 half reactions together. So 14 hydrogen ions plus 6 electrons plus dichromate Cr2O7 with a 2- charge. And, oops, before I draw the arrow, I better get my iron half in there. Remember, we multiplied that by 6, so I have 6 ferrous ions, the 2+ form of the iron. And that made 2 chromic ions plus 6 ferric ions, 7 waters, and 6 electrons. So my electrons are the same on both sides. That's what we were going for. Awesome. And nothing else is able to cancel out, so here is my balanced equation. Again, there's no way we could have balanced this using our inventory method or even the matrix method, because predicting these products could never happen unless we use half reactions. So when it's time for a half reaction, I'll let you know. There will be a clue. It will say use the half reaction method to balance the following complex redox reaction. Let's practice together in class and practice with other students who are in honors chemistry so that you can get this down. This is an important concept because now we're going to use the movement of electrons in redox reactions to build batteries. So, I'll see you guys in class.